Firstly, I hope everyone of you can access the recordings, right? Our previous sessions. If anybody is facing the issue in accessing, kindly drop an email because we have submitted everything to NPTEL team and drop an email to them so they'll be helping you how to access it. Okay, let me move forward with the summary. So here the week 6 our lectures will be discussing about the protein tertiary structure and quaternary structure along with the different applications or servers for protein tertiary structure analysis. Here, end of the session, we will be taking an PDB param demo as well. Okay, let's start with the protein structures. Protein structure is generally divided into four levels. As we know, primary structure, secondary, tertiary and quaternary structure, wherein tertiary and quaternary structures refers to 3D and higher order structures of protein. Coming to tertiary structure of a protein refers to the overall 3D shape of a single polypeptide chain. This structure is determined by interactions between the side chain of amino acids that make up the protein. These side chain can interact with a variety of chemical bonds and forces, including hydrogen bonds, hydrophobic interactions, electrostatic interactions, and disulfide bonds. These interactions, these side chain interactions cause the protein to fold into a specific shape, which is stabilized by the interactions between amino acids. The tertiary structure of a protein is critical for its function, and this shape of the protein determines how it interacts with the other molecules such as enzymes or receptors. Any changes in tertiary structure of a protein can affect its function and lead to a disease. Next is the quaternary structure, which refers to the arrangement of multiple polypeptide chains that make up the functional protein. So these subunits can be identical or different and are held together by various interactions including hydrogen bonds, disulfide bonds and hydrophobic interactions. This quaternary structure is important for the function of many proteins, particularly enzymes and signaling molecules. For example, hemoglobin, which is responsible for carrying oxygen in the blood, consists of four subunits. You can see the four subunits that are arranged in a specific way to allow oxygen binding and release. In summary, the tertiary structure refers to the 3D shape of a single polypeptide chain, while the quaternary structure refers to the arrangement of multiple polypeptide chains that make up a functional protein. So both these structures are important for a function of a protein and can be affected by the changes in the changes in amino acid sequence or environmental factors such as temperature and pH. Next is how do we get these 3D structures or a tertiary or quaternary structure of a protein. There are several experimental techniques that are used to determine the structure of a protein at different levels of organization. Here are some of the most common methods I'll discuss. First one is the X-ray crystallography, which is a technique that uses diffraction pattern of X-rays passing through a crystal of a protein to determine its structure. Here, the protein is purified initially and then the crystal is grown from it. Then this crystal is bombarded with X-rays and diffraction pattern, like see when these X-rays hit the crystal, a diffraction pattern is collected and this diffraction pattern is analyzed to determine the 3D structure of the protein. So this method is widely used to determine the atomic level structure of proteins. Later on we will discuss X-ray crystallography, what are the steps detailedly. The other methods are NMR, which uses behavior of atomic nuclei in magnetic field to determine the structure of a protein. And here in this, the protein is purified in this NMR method, and the protein is purified and then it is dissolved in a solution, and the solution is then placed in a strong magnetic field and radio waves are used to excite the atomic nuclei in the protein. The behavior of these nuclei is then used to determine the structure of the protein. The third method is electron microscopy, which uses a beam of electrons to determine the structure of a proteins. Next is the CD spectroscopy or circular dichroism spectroscopy, which uses the differential absorption of left and right circularly polarized light to determine the secondary structure of the protein. Here, the difference in absorption of the two types of polarized light is then used to determine the secondary structure of the protein. The last one is fluorescence spectroscopy, which uses emission of light by a fluorescent molecule to determine the tertiary structure of the protein. Here, the protein is labeled with a fluorescent probe and then a beam of light is passed through it. The emission of light by the fluorescent probe is then measured and data is used to determine the 3D structure of the protein. In summary of these experimental techniques, there are several experimental techniques used to determine the structure of the protein at different levels of organization, and each method has its advantages and limitations and is often used in combination to provide a more complete picture of the protein structure. Okay, let's discuss with the what are the steps. As I mentioned, X-ray crystallography is a powerful method used to determine the atomic level structure of the proteins. Okay, I'll be discussing some general steps involved in using X-ray method to determine the structure of the protein. The first step is the protein purification. The first step here is to obtain a pure sample of protein, and the protein is typically expressed in host organisms. The most commonly host organisms are E. coli or yeast, and then purified the protein which is overexpressed is purified using a combination of techniques such as chromatography, filtration and dialysis. And the next step is crystallization, where the protein is crystallized to form a regular and ordered array of molecules that can be analyzed using X-rays. Crystallization is difficult and time-consuming process that often requires screening many different conditions such as pH, temperature, salt concentration, and to find the optimal conditions of crystal growth. Next is the data collection. Once crystals have been obtained, they are mounted onto a goniometer and placed in a beam of X-rays. The X-rays are diffracted by atoms in crystal, producing a diffraction pattern on a detector. And the goniometer is rotated and diffraction data is collected at many different angles to generate a complete data set. And the next processes include data processing. So this diffraction data then must be processed to extract the structure of the protein. This involves this pre-processing or processing of the diffraction data includes several steps, including scaling and merging the data from multiple crystals, or calculating the phases of the diffraction pattern and building an initial model of the protein structure. Next is the model refinement. The initial model is refined using various computational tools to optimize the fit of the model to the diffraction data. This involves adjusting the position of atoms in the model to minimize the difference between the calculated and observed diffraction patterns. And the last one is validation, where the refined model is validated to ensure that it is of high quality and accurately represents the structure of the protein. This involves checking for the errors or inconsistencies in the model, such as clashes between atoms or unrealistic bond lengths or angles. In summary, this X-ray method involves purifying a protein, crystallizing it, and collecting the diffraction data and pre-processing the data to extract the protein structure, and refining the model and validating the final structure. It is a complex and time-consuming process, but it provides a highly detailed and accurate picture of the atomic level structure. So now I have discussed about the X-ray method. Can anyone mention using chat box or unmuting themselves what could be the major disadvantage or any disadvantage of using X-ray method? I hope I have mentioned three or four. I am audible, right? So can anyone respond? Am I audible or not? Okay, thanks for responding. So here I wanted to know, like I wanted you to answer what could be the major disadvantage of using an X-ray crystallography method, or any advantage, sorry, any disadvantage. Yes, it is a time-taking process. That's correct. And along with that, it's a time-taking process because it's very tough to get a proper crystal. But once we have the crystal in hand and out, it can provide a highly detailed and accurate picture of atomic level structure of proteins. As I mentioned, these experimental techniques has advantage and disadvantages both. Okay, next let me start with the PDB. So PDB is a database that contains information about three-dimensional structure of proteins, nucleic acids and other biomolecules. So here PDB is a database that stores the three experimentally determined structure for all the biomolecules. So the information source of PDB is the experiments. Here the PDB is a key resource for researchers in the field of structural biology, biochemistry and biophysics, providing access to experimentally determined structures of proteins and other biomolecules. The PDB database is maintained by WWPDB, which is Worldwide Protein Data Bank Organization. That is, it is a collaboration between several institutions, including RCSP, PDBE, that is PDB Data Bank in Europe, and PDB Data Bank in Germany. Yeah. The file format used by the PDB is a plain text format that contains information about the atomic coordinates of atoms in the protein and other biomolecules. Each PDB file represents a single structure and contains information about the type and sequence of the biomolecule, as well as the positions and properties of each atoms. The format of PDB file is divided into several sections, including a header section which contains a brief description of the structure, and the atom section which contains information about the atomic coordinates and properties of each atom, and the connect section which contains information about the connectivity between atoms in the structure. So here I'll be discussing about the atom section of the PDB file. So this typically contains the following information. The first is the atom serial number, next is atom name, residue name, chain identifier, residue sequence number, and XYZ coordinates of each atom, that is, these are the Cartesian coordinates. Then is occupancy, which is the fraction of time that atom is occupied by a particular conformation. And then is temperature factor, or it is also called as a B factor, which is measure of atomic vibrations or disorder. As I mentioned, the final session of a PDB is a connect section, which contains information about the bonds between atoms, as well as other types of connectivity such as hydrogen bonds and disulfide bonds. In summary, the PDB is a database of experimentally determined protein and biomolecule structures, and the PDB file format is a plain text format that contains information about the atomic coordinates and properties of each atom in the structure. The PDB file format is widely used in the field of structural biology, biochemistry, and biophysics, and has been adopted as a standard format for sharing and exchanging structural data. Next, we'll go with the what are the tools that are available for protein visualization. Now that we have structural data or structural data file in PDB, how can we download and use it? PDB provides an option for the users to extract the data. Once you extract the data, PDB file has to be visualized using the proper visualize to view the three-dimensional structure of the protein. So the popular tool is the PyMol, which is a powerful molecular visualization tool that is widely used in the field of structural biology. It allows user to visualize and analyze the protein structures in 3D and can generate high quality images and videos. PyMol is highly customizable and with a wide range of plugins and scripts available to extend its functionality. Next is Chimera X. So this is a next-gen molecular visualization program that is designed for interactive exploration of large molecular structures. Chimera is has wide range of features including support for virtual reality headset, interactive scripting and integration with other software tools as well. This also has an user-friendly interface that makes it easy to use for both uh, early and advanced users. Next is the VMD. VMD stands for Visual Molecular Dynamics, which is used for molecular visualization and analysis of large-scale biomolecular systems. It includes advanced features such as support for multi-graphics card, interactive molecular dynamic simulations, and scripting. VMD is used to visualize the dynamic or molecular simulations movie or analysis for the output of molecular dynamic simulations. Next is the other version of Chimera, and the other version is CN3D, that is designed for the analysis and visualization of molecular structures. This CN3D includes a wide range of features, including support for sequence alignment, protein folding analysis, and structure-based sequence analysis. And the last one is JMOL, which is a Java-based molecular visualization tool that is designed for the visualization and analysis of 3D molecular structures. It includes a wide range of features, including the support for multiple file formats, interactive scripting, and integration with other software tools. In summary, there are many protein visualization tools available to researchers, each with its own strength and weakness. These tools are essential for the analysis and interpretation of protein structures and are used in wide range of fields including structural biology, biochemistry, and biophysics. The choice of the tools depends on specific needs of the user. Its features and capabilities of each tool should be should be carefully considered before making a choice. Okay, here on I'll be discussing about the structural classes of proteins. So proteins have a diverse class of biomolecules that perform a wide range of functions in living organisms. Despite their diversity, these proteins can be broadly classified into some structural classes based on their overall fold and topology. The first one is alpha helix proteins. So these proteins have predominantly alpha helical secondary structure where the peptide backbone is tightly coiled into a helix. Examples of alpha helical proteins include keratins and myoglobin. The next is the beta type proteins where they tend to have predominantly beta sheet secondary structure where the peptide backbone forms an extended strands that are connected by hydrogen bonds. Examples of beta sheet proteins include immunoglobulins and beta lactamase. And the third class is alpha plus beta proteins. So these proteins have both alpha helical and beta sheet secondary structures. The alpha helices and beta sheets are arranged in a distinct region within the proteins, forming a distinct domain structure. Examples of alpha and beta proteins include triisophosphate isomerase and alcohol dehydrogenase. To summarize this slide, proteins can be classified into several structural classes based on their overall fold and topology. Each class has its own distinct characteristics and function, and understanding these structural classes is essential for understanding the structure and function of proteins in living organisms. Okay, let's see how computationally we can understand the, the structural classification. So SCOP and CATH are two widely used protein structure classification systems that provide an hierarchical organization of protein structures based on their evolutionary and structural relationships. So let's start with the SCOP, which stands for Structural Classification of Proteins, which is a database that classifies the proteins based on their structural and evolutionary relationships. So here the classification is hierarchical and is organized into the four levels. The first is class, full, superfamily, and family. Here, class means proteins are initially classified into one of the seven broad classes based on their overall shape and architecture. Next is fold. Within each class, proteins are further classified into folds based on their secondary structure, content, and arrangement. Third is superfamily. Four folds are further grouped into superfamilies based on their structural and functional similarity. And family. Finally, each superfamily is further subdivided into families based on their sequence and functional similarity. For example, the protein lactate dehydrogenase and the corresponding PDB ID is 1LDN is classified as follows in the SCOP database. The class of this protein is alpha and beta protein, and fold is a Rossmann like alpha beta or alpha sandwich fold. Next, the superfamilies, it belongs to the lactate or malate dehydrogenase, and the family is lactate dehydrogenase like family. Next is CATH. CATH stands for class, architecture, topology, and homologous superfamily, which is another hierarchical protein structure classification system that uses a combination of structure based and sequence based information to classify proteins. Similarly, this also gives information about class. That means here the protein are initially classified into one of the four broad classes. Next is architecture. Within each class, proteins are further classified into architectures based on overall shape and topology. Next is topology. So these topologies here classification is performed using the secondary structure, content, and their arrangements. Finally is the homologous superfamily, that is H. Each topology is grouped into homologous superfamilies based on their sequence and structural similarity. Similar protein PDB ID for the protein lactate dehydrogenase is classified as the class is alpha beta proteins and the architecture is Rossmann fold. Topology is NAD binding Rossmann fold like domain, and homologous superfamily is lactate or malate dehydrogenase like. In summary, both these databases provide an hierarchical organization of protein structures based on their evolutionary and structural relationships. SCOP uses combination and sequence and structural similarity to classify proteins, while CATH uses a combination of structure based and sequence based information. Both the systems are widely used in the field of protein structure analysis and provide a valuable information for studying the evolution and function of proteins. So here on, we have understood about the classification of protein tertiary structure and about the protein tertiary structure as well. Now I will be moving towards the analysis part. So first analysis step will be start with the contact maps. So contact maps are graphical representation of the pairwise interactions between the amino acids in protein structure. They are commonly used in protein structure prediction and analysis. So the construction of a contact map involves two main steps. The first step is to calculate the pairwise distances between all pairs of amino acids in the protein structure, where the distance calculation can be done using various methods such as Euclidean distance, Manhattan distance, or the Pearson correlation coefficients. So the distance can be calculated using the Cartesian coordinates XYZ representation systems. Yeah. Then these distances are then converted into a binary matrix where value of 1 indicates that the distance between two amino acids is below threshold, and a value of 0 indicates that the distance is above the threshold. So in this pairwise distances, 1 indicates that two amino acids are close, 0 indicates that two amino acids are far away from each other. The next thing is visualization of contact map. This can be done by plotting the binary matrix as heat map, where x and y axes represent the sequence positions of amino acids, and the color of each pixel represents the binary value corresponding to the pairwise distance. In addition to heat map, various other visualization techniques can be used, such as circular plots, 3D plots, or network diagrams. So there are several softwares or tools available for constructing the contact maps, such as Contact Map Visualizer, Contact Map Explorer, and Contact Map Analyzer. These, two, these tools provide various options for customizing and the visualization of the contact map. These customizations include adjusting the threshold for binary values, selecting the color schema, and adding labels and annotations. So interested people can try out these tools and their default pairwise distance matrix to see how these different tools provide different options for users. Next is the interresidue contacts in proteins, so which refer to the spatial relationship between amino acid residues in the protein structure. These contacts play a crucial role in determining the folding and stability of the protein, as well as their interactions with other proteins. Give me a second. Okay. Sorry for the pause. So there are different types of interresidue contacts, including hydrogen bonds, which are formed between hydrogen atom of one amino acid and the electronegative atom, such as oxygen and nitrogen of other amino acid. These hydrogen bonds are important for stabilizing the secondary structures, such as alpha helices and beta sheets. Next is the salt bridges, which are kind of electrostatic interactions between the oppositely charged amino acids, and these can play a critical role in protein-protein interactions and in stabilizing the tertiary structure of proteins. Van der Waal interactions. These van der Waal interactions are weak and short-range interactions between the non-polar amino acids, and van der Waal interactions helps to stabilize the packing of amino acids in the protein core. So can anyone tell me what is the term used to represent this packing of non-polar amino acids into the protein core? What is the process called during protein folding? I'll repeat the question. So this packing of non-polar amino acids during protein folding has a particular name. Can anyone mention what is that name? Yeah, the name is hydrophobic collapse, where these nonpolar residues are moved into the core of the protein. Okay. Next is the disulfide bonds. So disulfide bonds are the covalent bonds between two cysteine residues, which can occur within a protein or between two different protein molecules. So this identification of interresidue contacts in protein can be done using experimental techniques such as X-ray crystallography or NMR. However, as we discussed, these are time consuming and difficult methods. So therefore, computational methods have been developed to predict the interresidue contacts from protein sequence or structures based on statistical or machine learning models. These predictions can be useful for understanding the protein folding structure and functions. So here these three are the type of contacts that are analyzed in a protein structure. So these are short range, medium range and long range and contact different types of spatial relationships between amino acid residues in the protein structure. Coming to the short range contacts, these are typically defined as the contacts between amino acid residues that are close in sequence, usually within a few amino acids of each other. That is one or two amino acids difference. So these short range contacts are critical for forming and stabilizing secondary structures such as alpha helices, beta sheets, and are typically formed through hydrogen bonds and van der Waals interactions. Next is the medium range contacts. So these contacts are the contacts between amino acid residues that are farther than the short range contacts in sequence, usually separated by 4 to 10 amino acids. And these medium range contacts can play an important role in stabilizing the tertiary structure of proteins, and they are typically formed through combination of hydrogen bonds, van der Waals interactions and electrostatic interactions. The third ones are the long range contacts. So usually these are the contacts between the amino acids that are distant in sequence and usually separated by more than 10 amino acids. So these are critical for maintaining the overall structure and function of the proteins and are typically formed through combination of hydrogen bonds, van der Waals interactions, electrostatic interactions such as salt bridges or disulfide bonds. So the identification of short, medium and long range contacts in protein can be done using experimental techniques, but computational methods have been developed to predict these contacts from a protein sequence or structure based on statistical or machine learning methods. These statistical or machine learning predictions can be useful for understanding protein folding, structure, and function, as well as for designing new proteins with specific properties. Next is the accessible surface area, which refers to the portion of the protein surface that is accessible to solvent molecules. The assay is important for understanding the protein-protein interactions, ligand binding, and protein stability. The calculation of ASA is typically based on solvent excluded surface model, which is shortly called as SCS model, which assumes that the protein surface is formed by the boundary between the protein and surrounding solvent molecules. To calculate a solvent excluded surface, a rolling probe algorithm is often used. The rolling probe algorithm involves placing a probe up sphere of given radius. Usually, if we want surrounding, if we consider water, then we take a probe size of 1.4 angstroms. Or if we consider for a membrane proteins, where we consider CH2 group, there we take a probe size of 2. Then this probe or the rolling is done along the surface to identify the proteins where the sphere first touches the protein. The points where probe touches the protein surface are considered to be the surface atoms, and the remaining points are considered to be the interior atoms. And the ASA is then calculated by summing the surface areas of all the surface atoms, and surface area of each atom is determined by the area of the sphere that is not covered by the protein. So this area can be calculated using geometrical formulas such as formula for area of a spherical cap or area of an annulus. The calculated accessible surface area can be expressed in terms of absolute values, that is Armstrong square, or as relative values known as ASA ratio. The ASA ratio is calculated by dividing ASA of a given protein by ASA of a reference state, usually completely unfolded state. Of the reference state is completely unfolded polypeptide chain or a random coil state. In summary, the rolling probe algorithm is a method for calculating the accessible surface area of protein, which is important parameter for understanding the protein structure, function and stability. There are several methods and tools available to calculate solvent accessibility of proteins. So I'll discuss some of them first with the N-axis, which is widely used one. So it uses a rolling probe algorithm to calculate the solvent accessible surface area of a protein, and output provides the information about solvent accessible surface area for each residue in the protein as well as overall solvent accessible surface area of protein. Next is the DSSP, where it calculates the accessibility of each residue based on the position of the residue in its protein secondary structure. Yeah, we have discussed about DSSP during the last class as well, where we are talking about analysis of protein secondary structures. Yeah, here DSSP uses a database of known known protein structures to assign secondary structure to each residue, and then calculates the accessibility of each residue based on its position in the secondary structure. Next is the NetSurfP, which uses a neural network model to predict the probability that each residue is solvent exposed or buried. And the output provides information about the predicted solvent accessibility of each residue. Next is RVPNet. So where RVPNet uses a recurrent neural network model to predict the probability that each residue is solvent exposed or buried. The output provides information about the predicted solvent accessibility of each residue in the protein. And the last one is Scratch. Scratch is a suite of web servers that can predict various properties including solvent accessibility. Even Scratch uses a neural network model to predict the probability that each residue is solvent exposed or buried. In summary, there are several methods and tools for calculating the solvent accessibility of proteins, including softwares that uses experimental data as well as web servers that use predictive models based on primary sequence. These tools can provide valuable information about structure, function of proteins as well as their interactions with. This is a last slide for the summary. Here I will be discussing briefly some of the protein tertiary structure features, and similarly we will be having some sample problems on these as well. The first thing is buriedness, which refers to the extent to which the given residue or region is buried within the protein structure and shielded from the solvent environment. It is an important structural property that can use to predict the functional roles, interactions and stability. The degree of buriedness can be quantified using number of different metrics including solvent accessible surface area, relative accessible surface area and packing density. So here now I have mentioned about packing density. Let's discuss about packing density, which measures the tightness of packing of atoms within the protein core and is calculated as the ratio of van der Waals volume of atoms within a given volume to the volume itself. So van der Waals volume of atoms divided by the volume of the protein. So a high packing density value indicates that a tightly packed protein core with less space for water molecules to occupy, while a low packing density value indicates a more loosely packed protein core with more space for water molecules to occupy. In summary, buriedness in protein can be calculated using solvent accessible surface area or relative solvent accessible surface area. They can provide valuable insights into the structural and functional properties and can use to predict stability. Next is the transfer free energy. This transfer free energy can also be expressed in terms of partition coefficient, so which is the ratio of concentration of solute in one environment to the concentration of another environment. And this transfer free energy is an important parameter in many biological processes such as protein ligand binding, protein-protein interactions and membrane transport. It can be used to predict the affinity of a ligand for a protein, stability of a protein complex, and permeability of a. Next is the contact order, which is a measure of local compactness of protein structure, and it is defined as the average sequence separation between amino acid residues that are in contact with each other. It is an important predictor of the folding rates of protein. We'll solve a problem on contact order as well as a long range order, which refers to the regular and repeating arrangement of amino acid residues in a protein structure over long distances. This long range order is characterized by the presence of secondary structure elements such as alpha helices, beta sheets that are stabilized by hydrogen bonding between them. This long range order refers to the regular or repeating arrangement of amino acid residues in protein structure over long distances. It is important for stability and functions of protein structures and can be visualized and quantified using various tools and metrics. Yeah, I now completed this summary part. So before moving into the quiz part, I would like to take any questions if you are having that we have discussed so far. Regarding the formulas of what features we have discussed, I'll be explaining the formulas and we'll be solving a sample problems in this quiz. I just given an introduction to the features analysis part where we'll be solving a problem on analysis part in next part. Here I'll pause for a minute to take any questions. Okay, yeah, if no questions, I'll be moving. The first question is flexibility of atoms in protein structures are identified with. So, what parameter of a PDB file represents the flexibility of atoms? Yeah, you can answer using chat box. Okay, sorry. Yeah, there is a question regarding the topology. Yeah, topology is nothing but the surface. So when we talk or when we tell about your protein topology or any topology, so what we mean here is a simplified description of its fold. Like means when we tell what is the topology of alpha helical means it has a spring-like structure or a coil-like structure. And there are many different situations where topology has been uh, uh, used. For example, in generally we also use this topology term that doesn't change or deform. Yeah. Okay, moving on to this solution, I have got different answers. Nice. Yeah, one thing is clear from the options that these all belong to the PDB file format. So these are the components that are present in PDB file format, of which the first XYZ are Cartesian coordinates, temperature factor, or it is also called as B factor. Here, the correct answer is temperature factor because this is a measure of mobility of an atom or a group of atoms in a protein or other biomolecules. And this also provides information about the flexibility or disorder of the molecule at a given position. The temperature factor is a measure of average displacement of an atom from its mean position in the crystal, and it is expressed in the terms of Armstrong square and usually takes a value between 0 to 100. So 0 indicates that the atom is in fixed position, while 100 indicates that the atom is highly mobile and could be in any position within its thermal vibration. Okay, next. Next is regarding the X-ray crystallography question. So what information directly the X-ray method provides us? Okay, yeah, focus on the question. It tells what information it directly provides us without any pre-processing or is required, or without any further processing further steps. What is the direct output from an X-ray instrument or an X-ray method? Okay, yes, yeah. As we know, in the X-ray method, uh, a crystal of molecule is exposed to the intense beam of X-rays, and these X-rays interact with the electrons in the crystal and are diffracted in a characteristic pattern, which can be measured and analyzed to determine the position of the atoms in the molecule. One of the key results of X-ray crystallography is electron density map, which shows the distribution of electrons in the crystal. And this electron density map is calculated by analyzing the diffraction pattern of X-rays and some other, with the help of some other mathematical methods, to determine the electron density at each point. And this electron density map provides an information about the structure of the molecule, including the position of individual atoms, orientation of functional groups, and overall shape of the molecule. Followed by generation of electron density map, we have a step called model building. I didn't mention before. So here the purpose of model building is the positions of the atoms in the molecule can be determined by fitting to known models of individual atoms or small groups into the electron density. So where this electron density is used is referred to other electron density, and then this models has been fit. Yeah, here the solvent accessibility of residues alanine 7, uh, uh, valine 9, aspargine 10, and alanine 11 in a protein are given here. So based on these given values for these 5 residues, can you tell what are the residues that are located on the surface and which are not? So here I am asking for residues that are on surface. So given solvent accessibility for any 5 residues, can you determine which are solvent exposed and which are buried? Here based on the solvent accessibility options. Okay. Here, solvent accessibility for the exposed or the residues that are on surface will be high. So here when we see the scale of residues, we have 56 and 78 followed by 0.1, 1 and 2. So here the clear-cut division for residues and buried residues has been given based on the solvent accessibility values. So here the answer is B. So the exposed residues tend to have more solvent accessibility values. The next question is also on solvent accessibility. So given the accessibility of residue arginine 74 in folded and extended states, can you calculate the percentage accessibility? I hope everyone knows the percentage accessibility. You can mention what is the value. So given accessibility of a residue in folded and extended states, can you calculate the percentage accessibility? So in general, you keep on calculating. I'll be giving a brief about percentage of accessibility, which refers to the degree to which a particular residue is exposed to the surrounding solvent in a folded protein structure. I'll wait for a minute for you to calculate. So given accessibility of a residue in folded and extended state is nothing but the unfolded state, can you calculate the percentage of accessibility? Okay, I got one answer, 47.27. Okay, I'll wait for others to respond as well. Okay, since I got started receiving, I'll give a hint. The percentage of accessibility can be calculated by dividing the solvent accessibility of a residue by the maximum possible solvent accessibility for that residue. That means solvent accessibility of a residue at particular moment divided by the maximum accessibility of that residue. Then we multiply this value by 100. Yes, the answer is okay, 47.27 or 47.2. So where it is calculated by using accessibility of a arginine 74, that is 78 in folded state, 75 divided by maximum accessibility. So the maximum accessibility or solvent accessibility can be acquired in extended state or unfolded state. So here 78 divided by 165 into 100, so which gives answer 47.2. Yeah, similarly I have given explanation for this which you can refer those who didn't understand. Yeah, next is we'll start with the buriedness, how to solve. If a protein has 20 alanine residues and 5 of them are on surface, okay, sorry for the repeat in the lines, then can you calculate the buriedness of that alanine residue? I'm repeating the question again. A protein has 20 alanine residues and 5 of them are on surface. So can you calculate the buriedness of that residue? I'll give you time to solve. Okay, 25%. Let's see. Any other answers other than 25%? Okay, buriedness is a concept that is related to the interior of the protein. So here, uh, okay, here we have given, yeah, I got the answer 75. Here we have given number of alanine residues in the protein and number of alanines that are on surface. So here is the formula. Okay, I'll be solving this using Google Jamboard. So given number of give me a second, I'm setting up my Google Jamboard. It's okay. Okay, now given the number of residues in protein are 20 and that are on surface are 5. So which are in interior will be 15. Has its buriedness BR is given by interior proteins by N. So 15 by 20. That equals to 3 by 4 or 75%. Okay, just give me a moment. Yeah, I hope this is clear. Any doubts on this? They can ask now. I can re-explain. Yeah. So this is the formula. The buriedness is given by number of residues of I type in the interior of the protein and total number of residues of I type. For example, buriedness of alanine. That is the question. So number of alanines in the interior of the protein divided by the total number of alanines in the protein. Next is given a protein, can you calculate the transfer free energy? So I have given the formula as well here. So using the formula, can you calculate the transfer free energy? And the description for the F has been given in the paragraph provided over there. Let's check. I started receiving the answers. Okay, here the partition F is the partition coefficient which can be computed from the occurrence of the residue in the interior of the protein and to that of in the surface. So number of times the protein is in the interior divided by the number of times the protein is in the surface. Oh, sorry, residue amino acid is in the surface. Okay, before moving on to the solution, yeah, this is the given formula, and the partition coefficient F can be calculated as 15 divided by 5, that is 3. So substituting the values of R into 3 is 300 into ln of 3, you will be having the transfer free energy. So here R is the gas constant, so here the answer will be minus 654.88. It's okay, here I got similarly close answer. Can anyone tell what will be the units of delta G here? So kilocal, only kilocal. Why not a kilocal per mole? Since partition coefficient is also a normalized value, it is unitless. So kilocal per mole per Kelvin is multiplied by Kelvin. So final units of delta G transfer will be cal per molecule. Okay, next question we'll be solving a contact order. If a protein has 50 residues and 200 contacts, now we are trying to calculate a contact order for residue alanine 45. So which has contacts with residue 46, 47, 44, 71 and 60. So based on this information, can you calculate the contact order for residue 45? Okay, if it feels tough, I'll provide with a formula. So contact order is summation of sequence separation between the residues I and J divided by the number of residues in the protein divided by the number of contacts in the. Oh, contact order is a statistical inferred value which is calculated. It's not the sequence of contact or nearest neighbor kind of thing. It's a value that is widely used in current day prediction models of protein stability or protein binding affinity with other ligands or with other proteins with carbohydrates and everything. And this particular feature has been developed by the Professor Michael Gromia, and several other details have been available in the textbook Protein Bioinformatics from Sequence to Function. And this textbook Yeah, the distance cutoff, I have selected these are based on distance cutoff. So when we know them, this 45, 46, 47, 44, 71 is within the distance threshold. You can calculate the thing. Consider them, they are within the distance threshold. Calculate the contact order. So in contact order, the value of S is sequence separation. So think alanine 45 and glycine 47 are separated by two residues. So the value of S here will be, in case of alanine 45 and glycine 47, is 2. Okay, let us move on to the solution. So okay, given first we have to get S of ij. So our residue is 45. So the other residues what we have is 46, uh, 47, 44, 71 and 60, I feel. Yeah. Now the Sij values will be 45 minus these values. That to absolute values, not regular values. So we get 1 plus 1 plus 2 in the case of 47. Sorry. 1 plus 2 plus 1 plus 26 plus 15 divided by L is number of residues, L into N. So we'll add the values of now. So 45 divided by 50 into 200 contacts are there, where L stands for number of residues, N stands for number of contacts. Okay, now can anyone mention the values? So the value will be 0.045. Okay, sorry, I didn't share the screen. So here the value is 0.05. So now let's move on to the long range order calculation. So this calculation is also similar to the calculation of contact order with slight difference in the formula. So here is the formula where it is calculated by considering a binary value system to the connecting and non-connecting residues if they are within the sequence cutoff or not. So this is the summation of n of ij divided by n, where capital N is the number of total residues in the protein and n corresponds to 1 if sequence separation between the two residues is less than is more than 12. If they are separated more than 12 is 1, otherwise 0. Yeah, someone asked we need distance for calculation. Yeah, we need distance for calculation to analyze the context. But once we know the context, we need only sequence separation for calculating the long range order or the contact order. Yeah. Okay. Now we have a residue for sorry, your residue 45, which is interacting with 44, 40, sorry, 46, 47, 71, and 16. So according to that formula, long range order will be divided by number of residues, that is 50. Then, so in the case of 45 and 44, we have sequence separation of 1. So if sequence separation is less than 12, so we need to take 0. Next, again 46, here 0. 47 is 0 because the sequence separation is less than 12. In 71, the sequence separation is 26, so I take 1, and in 60 it's 1. So that means 2 divided by 50. So it will be 0.04. Sorry. Yeah. Next, other concept is given hydrophobicity values, can you calculate the hydrophobicity of a surrounding hydrophobicity of a residue which has two alanines, one valine, one threonine, one serine, and one glutamic acid. Below are the amino acid short forms and their hydrophobicity values. This is a pretty straightforward question. I think I'll show you the formula also how to calculate, which makes it easy for you. without wasting any time, let me move on to the solution. So here we have two alanines and value of hydrophobicity scale of alanine is given. Then we have one valine and value of one valine is given. Likewise, number of amino acids and their corresponding hydrophobicity values were collected like this. And then we finally sum up them to have minus 4, 4 minus 7, that equals to minus 3. So the answer is minus 3. So here are some basics questions. So I have last 3 or 4 couple of questions. If you answer, we can wrap up with the class. Okay, yes. The answer is C, where we have discussed them. Here is the next question. This is next question. Which method provides the information on both secondary structure and solvent accessibility? So this is the method that we have discussed today as well as in the previous class. No answer for this. Okay, it's DSSP. Where is the directory of secondary structure predictions? So it is both useful for predicting solvent accessibility and secondary structures. Next is the PyMol based question. PyMol can be used for okay. Yes, PyMol is used for protein structure visualization, and also it provides option for us to compute bond angle, bond length and torsional angles, and it also helps to prepare high quality figures for our publication or other analysis or distinctive purposes. Yeah, this is the last question for the day. So proteins containing alternate alpha helices and beta strands belong to which class? They belong to alpha beta class. That is the third class in structural classification that we have done. So I'm done with my part here. So I would like to take any questions you have or regarding the calculation or what we have done. If no questions, thanks for attending the session and thanks for your patience throughout the session. You can leave if no questions. If you have any questions, please unmute yourself or you can use chat box. Question number 3. Okay, I'll do it. Once again, I'm repeating. The session is done for today and open for questions. Thanks for attending and your patience. If no questions, you are free to Yeah, I'll do that hydrophobicity as well. Yeah, question number 3. Here we have 5 residues. Yeah, in the 5 residues, for each residue we have a solvent accessibility. So the condition here is when we when a protein is exposed outside it or it is on the surface, it has higher solvent accessibility value. So when we consider here, we can divide them into two classes. One with like two residues having higher solvent accessibility of 56 and 78, and other three residues having lower ones. So based on these solvent accessibility values of these residues, we can classify uh, 8th and 11th residues are on the surface. Rest all may be in the interior. Hope I am clear in this explanation. Yes, okay, let me move on to the. Yeah, this is hydrophobicity. Where? So, where I have given a residue and its number of its surrounding residues. Like I'm telling, it has two alanines, one valine, two threonine, and one serine, and one glutamic acid. The calculation. Yeah, this one, right? Okay. Thanks for confirming. So here the formula is summation of number of surrounding residues of type J. Think if I am thinking to calculate alanine. So number of alanine surrounding the 27 residue. So I have two alanine residues where HI is the hydrophobicity index or hydrophobicity values for alanine. So which is given as 1 here. So considering for alanine, so the alanine value is 1. So here I'll have 2 into 1 followed by 1 valine, and value for valine is 2. So 4. So till now I got 4. That means a value from here and value from here using this formula. Next I have 2 threonines. That means 2 into the number of threonines multiplied by what is the value, that is minus 1. So now 4 minus 2. Next we have 2 glutamic acid. So that is 2 into what is their value. So it is again minus 2. So 2 into minus 2 gives rise to minus 4. And then lastly we have 1 serine. The value of serine is minus 1, then minus 1. So overallly this value will give minus 3. So where here Nij is number of uh, surrounding residues of type I, like alanine, number of alanine surrounding threonine 27, or number of valines surrounding, number of vitamins. So each and we sum up to this value. Yeah, am I clear in this explanation? Okay, thank you for asking questions as well. Yeah, generally alpha helix and beta sheets are two different protein secondary structures. So they are in structurally different and they have different hydrogen bond pattern, which gives them that structural topology or structural conformation. Okay, any other question? I think I answered Darshana's question.